So far, we have been discussing what happens when the processor is requesting data or instructions from the memory, and those words have to be fetched from the cache. And what happens when there is a hit and the update to the recent usage in the cache, and what happens when there is a miss, that the block that contains the word has to be fetched from the lower level in the memory hierarchy. In this lecture, we'll talk about writes. What happens when the processor needs to do a write to a memory location, and the memory location may or may not be in the upper level in the cache. So there are several strategies that we can use in this situation, and we're going to review these strategies in this lecture. So the question that we are addressing in this lecture is what should happen when there is a write to a memory location. The first policy that we will study is called the write back policy, and we're going to look at what happens in this policy when the processor is trying to do a write, which means a store, and the location that the processor is trying to store to is in the cache. And we are considering a memory hierarchy with only two levels because it's easier to discuss the policy in two levels of memory hierarchy, but the same policy can be applied to any levels in the hierarchy. It's just that the write will gonna go then from the L1 data cache to the L2 cache, or from the L2 cache to the L3 cache, from the L3 cache to the memory, etc. So if the processor wants to write and the location is in the memory, and we are using a write back policy, then the processor will only write to the cache and it will not gonna write to the memory itself. So the write will gonna stay in the cache. And now we have a situation where the cache line or the cache block that is in the memory is stale because the most recent version of that block is in the cache. So to account for that and to be able to follow up with it, we're going to use an additional bit in the cache. This bit will be associated with each one of the blocks in the cache, and this bit will say whether that block is clean or dirty. A clean block is a block that is identical to the block that's in memory, so a block that has not been changed since the last time that it was brought from the memory. A dirt block is a block where at least one bit in the entire block has changed since the last time that it was fetched from the memory. So when I write, when I do a store, I'm storing only a single word. Remember, a block in the cache contains multiple words. I only write into one of them, but I mark the entire block as being dirt because at least one bit of the block may have been changed. So in the write back policy, what's going to happen is that at some point there will be an eviction of that block from the cache. I'm going to be replacing that block to make room for another block. At that point, I must write back to the memory when the entry is evicted. And that is why the policy is called a write back policy. So this is the write back policy. An alternative policy for that is what's called a write through policy. In a write through policy, when the processor needs to write into the cache and the data is in the cache, so the line is in the cache, then what the processor is going to do is, what the system is going to do is to do that write into the cache block and also write into the memory. So we're going to write to the cache and to the memory. And in this case, the memory is consistent at all times. The memory never going to have a value that's not compatible with the value that's in the cache. This is called a write through policy because there is no need for a dirt bit, and it's called a write through policy because I'm writing through the cache and into the memory. So those are the two policies for when I am trying to do a write and the block that I want to write to is in the cache. What happens if the block is not in the cache? If the block is not in the cache, then I can have a write allocate policy. In the write allocate policy, the processor is going to issue a write, and the write, I get to the cache, and the line is not in the cache, so the block is not in the cache. In this case, what the processor going to do is fetch the entire block from the memory, make room for it in the cache, and then write on that block. So this is the equivalent to the write back policy, but we call it write allocate because it's for the case of a miss. And then we're going to write it. So now the line is dirty, and I'm going to make I'll make a note that the line is dirty. So this is the write allocate policy. And the write allocate policy makes sense to use with a write back because, of course, when I replace that block later, I'm going to have to write it back to memory so that I have a new block there. The other strategy that I can have when I have a miss in the cache is called a write around policy. In the write around policy, I have a similar situations before. The processor is trying to issue a write. It's a store operation. And the block is not in the cache, so the processor will take that word, it's a single word that the processor is write, and we're going to write only to the memory. It will not going to write into the cache. So in this case, again, there is no need for a dirt bit, and this is a write around with a write through, because so it's called a write around because in the case of the miss, I write around the cache, but I'm going to be using this policy with a write through because I'm not going to have a dirt bit and I'm not going to have dirt values in memory. So one of the issues that we have in all cases with writes is that it may take a long time to write into the memory may be slow, and the writes will be in the way of loads and the processor needs the value from the loads to continue the execution. So one of the things that, so what we have is this situation here. We have the processor and the cache operating, and they are operating at full speed. And I have a situation where I need to do a write, and the write is in the way of other loads that I want to have, and the write will take a long time. So what the solution to this is to create a new structure between the cache and the memory that's called a write buffer. And when the cache needs to do a write, it does not write direct to the memory. Consider in the case of the write back policy that the write back policy will going to be evicting a block at the time that it needs space for a new block that it needs to bring from the memory. So the processor is already waiting because there was a miss. I'm going to do an eviction of a block when there is a miss, and I need to bring a new block from the memory. Now, if I have to complete the write before I can fetch the new block, that may take a long time. So what I'm going to do, I'm going to write in the write buffer. The write buffer will be small and close to the cache. And in this way, I can do the write to the write buffer very quickly. And then I can proceed with the load. So I made space in the cache, and I can load the new block from the memory, put in the cache, provide the data to the processor, and the processor will continue operating. At some point, there will be enough time or enough resources between the write buffer and the memory, and at that point, I write from the write buffer to the memory, and I clear that entry from the write buffer. The issue now is that for every load that I do, the value that I'm trying to load, or the block that I'm trying to load, may be in the memory, but it may be in the write buffer. It's actually, there is a high probability that it may be in the write buffer because I am likely to be fetching again a block that I recently evicted because it's a block that not too long ago I was accessing. So in every read, I must check the write buffer to see if the data that I'm looking for is in the write buffer, if the block that I'm looking for is in the write buffer. So that's another reason that the write buffer must be small, because in every load I have to do what we call an associative search of the write buffer. I need to check every single entry in the write buffer to see if it is the one that I want to load right now. If I find it there, I can provide it to the cache and continue, because this is the most recent copy. If I do not find it there, then I'm gonna read from the memory. Just to conclude this lecture, we're going to take a look at one example of a real cache. This is the Intrinsity FastMat cache. It's an example. It's an embedded MIPS processor. The instructions and the data accesses it does access instruction data in each cycle. It has a split cache, separate iCache and Dcache. Each has 16 kilobytes, 256 blocks by 16 words per block. The Dcache is a write through or write back. It can be configured. And on a spec 2000, the miss rate for a spec 2000 would be 0.4% for the iCache and 11.4% for the Dcache. It's very common that the Dcache you're going to have a higher miss rate than the iCache because access to the data is not as contiguous or doesn't have as high locality as the access to the instructions. And the weighted average miss rate for this cache is 3.2%. So in the Intrinsity FastMat, if I have a memory address that has 32 bits, my data will be 512 bits in each block. And I'll have 256 entries into the cache. And I'm going to have a tag, and I have a valid bit. And when I do an access, I will take the index to access which entry in the cache I am accessing. And then I'll compare. This is a direct mapped cache, so there are not multiple sets. I compare the 18 bits of the tag with the 18 bits that the tag stored into the cache. And that will tell me whether it was a hit or a miss. And I provide that information to the processor. And now I have a MUX that will select one of the blocks according to the bits that I use. I call those the word offset. So I have divided the offset into word offset and byte offset. I have two bits, the bit 0 and 1 for the byte offset that tells me which byte inside the word. And now this way I select the word and I provide the word as data to the processor. Another example is the Intel Core i9 9900K. That's the Coffee Lake processor from Intel. This processor has a L1 instruction cache of 256 kilobytes and the Dcache also 256 kilobytes. And they are 8 by 32. They are 8-way set associative. And the L2 cache is 4-way set associative, 8 by 256. And the L3 cache is 16-way set associative. The other example that I have is the IBM Power 9. The IBM Power 9, remember IBM is now about sometime in the future we're going to release the Power 10. Power 9 is the most recent processor from IBM. Here are some numbers from the Power 9. It has a L1 instruction cache of 32 kilobytes. That is 8-way set associative, L1 data cache of 32 kilobytes that is also 8-way set associative, and L2 cache 258 kilobytes for each one of the simultaneous multi-threading cores. And it has an L3 cache of 120 megabytes that is divided into 12 regions or chunks. Each one of them is 10 megabytes, and it's a 20-way set associative cache, so there are 20 blocks per set. And it has 7 terabytes per second on-chip bandwidth to access this L3 cache. So these are some concrete numbers to the idea with these examples. One is a small processor from a long time ago, the other is a fairly recent Intel processor, and the other is the most current IBM processor. Just to give you an idea of what those values are for real processors that are out there in the market, on the market.